Okay, hi class, this is the lecture on molar enthalpies. This was for the class that had the fire alarm, or if you just want to review it, I'll just go through it. So here's my Twitter name, it's at Mr. Saleh LMA. So just a few rules: don't direct message me, I'm not going to respond to those, and don't include me in tweets that are unrelated to chemistry. If you have any questions, or if you say I'm having trouble with X, Y, and Z related to the unit, that's perfectly fine, that's what I'm looking for. And just make sure you use the hashtag SalehChem. I can compile all these tweets, I can use it to make a review that's based on what you guys need to focus on. Okay? So these are two videos right here we had for endo and exothermic reactions. I showed them both in both classes, so we'll just skip that for now. Stated each reaction is exo or endothermic. Very quickly I'll run through these. Kerosene burned in a jet engine, so any combustion reaction you're looking at exothermic because it releases a lot of energy. Ice melting, so this is going from a solid to a liquid state. If you just think about it with a bit of common sense, ice is cold, it needs heat to become a liquid, so it's endothermic. Liquid ethanol being vaporized, so you're going from a liquid to a gas state. Think about intermolecular forces. You have to break those forces in a liquid to make it a gas, so energy is required. So this is also an endothermic reaction. And finally, the beaker gets hot when two substances are mixed together. This is an exothermic reaction. A few keywords that you should be on the lookout for during review or for a test. If it says the reaction absorbs energy or absorbs heat, that means it's an endothermic reaction. Okay? If it says heat was released or energy was released, this is an exothermic reaction. These are just some keywords that you should keep a heads up for. Okay, molar enthalpy. So molar enthalpy is the energy change or the enthalpy change associated with reactions involving only 1 mole of substance. Okay, so here we have the delta H combustion, or that's what it says in the textbook, but I think it really is better to say the delta H formation. Okay, so we have 1 mole of H2 plus half a mole of O2 to make 1 mole of H2O plus 241.8 kilojoules of energy. Okay, now you'll notice both signs here are different, but it's with reference to the same question. When we're stating it in the reaction itself, we're saying that energy was one of the products. This is an exothermic reaction, so energy was released as a product. When we state the delta H value separately outside of this reaction right here, then we say negative 241.8. The negative sign indicates that it was an exothermic reaction. Okay, so just be mindful of which sign you use. Different types of reactions. So just one thing to clarify right here, this little subscript X, this stands for the type of reaction. So we have some different reactions right here. Solution. So this is 1 mole of salt being drawn into a solution. Okay, so that's a type of reaction that's being stated over here. Here we have very familiar combustion. So this is combustion of 1 mole of CH4. So this is with reference to CH4, 1 mole being burned. That's the type of reaction that's being stated over here. We have vaporization, freezing, neutralization. You'll notice it's the same equation or the same reaction, but there's two of them stated, and that's because it's with what reference you're looking at. First example right here, we're looking at 1 mole of H2SO4. So with reference to the acid, this is 1 mole of reaction. Okay. If we do this again, then we're looking at it with base. With reference to 1 mole of base, we're looking at the same reaction, but the energies could be different. Okay. One thing that a few students did ask about was the use of the half or fractions. Using fractions to balance equations is perfectly fine. I know we said in grade 11 we're looking at whole numbers. Using fractions is perfectly fine. It's just it becomes a problem when we're doing math. That's why generally we tell students to avoid using fractions. But in cases like this, for thermodynamics or for thermochemistry, it's perfectly fine. We're just trying to make a point that the 1 in reference is already 1 mole. Okay? And then finally there's delta H of formation, but we'll look at this in section 5.5, so don't worry about it for now. As stated before, if you're going to put your delta H value separately outside of the reaction, be very mindful of the sign that you choose. If you state it as a negative, then we say it's exothermic, and if we say it as a positive, then we say it's endothermic. Okay? So one example right here, carbon monoxide plus hydrogen gas gives you methanol and 128.6 kilojoules of energy. This one would be exothermic, okay, because energy is a product, is being released with the methanol. Okay. H2O plus 285.8 kilojoules gives you hydrogen gas and oxygen gas. So this is saying this is an endothermic reaction. Why? Because energy had to be included with the reactant for the reaction to go to completion. So we had to input energy. Okay. Over here, magnesium, so 1 mole of magnesium plus O2 gives you magnesium oxide. Separately stated is a delta H value of negative 601 kilojoules. If it's separately stated and it's a negative, that means it's exothermic. That's the rule that we follow. Now, a question will arise, what if I had more than 1 mole? So let's say we had 2 moles of magnesium. Then we simply double this value, so we just times it by 2. Okay, because this delta H is with reference to 1 mole of magnesium. That's the value. If we have 2 moles, then obviously we have to double this value. So we'll get about 1200 kilojoules. Okay, so this this equation, very important to copy down. Delta H, so your total enthalpy change, is equal to the number of moles of reactant that you have times the enthalpy change value. Okay, so if we look at this example right here for magnesium, we have 600, so minus 600 kilojoules, that's our enthalpy change for 1 mole, and let's say we had 2 moles, and for our N we will substitute 2. So then our total value for delta H would be 1200. So minus 1200. Okay. Now page 307, 308, they have sample problems. The textbook, it goes through it step by step. I would highly recommend that you look at it and you work through those before moving on forward. Okay, on Monday there's a calorimetry lab. So there's 3 assumptions that we're going to work with. The very first 2, assume that no heat is transferred out of the styrofoam cup, and assume that no heat is absorbed into the styrofoam cup. So we're going to assume that it's a perfectly closed system, that nothing gets in and nothing gets out. However, if on the lab it states that styrofoam has a specific heat capacity, well, now you got to disregard these first 2 assumptions. If a value is given, then you have to take it into consideration. If nothing is given, then we assume that it's not going to let any heat go. The third assumption, assume that the solution has density and specific heat capacity of water. So very likely we'll be working with acid, so we're just going to assume that the acid is similar to water. So that's 1 gram per milliliter. So if, for example, you use 50 milliliters of acid, then we just say that's 50 grams of acid. And also the specific heat capacity, we're just going to assume that it's the same as water, 4.18 joules per gram per degree Celsius. Okay? Okay. And this is where this equation comes into play for the lab. We looked at delta H separately and we looked at Q separately. So delta H equals N times delta HX and Q equals MCT. Now these things are for reactions that occur separately, and we're going to assume that these happened with nothing around them. But that's not how the real world works. The real world, you have your reaction and you have your surroundings, which is represented by Q. So a reaction has to take place in some sort of surrounding. It doesn't happen by itself. So this is where you can mix the 2 equations together. So therefore we say delta H can equal to MC delta T. Now the delta H part, so this is number of moles times the molar enthalpy, represents the system, or what we would term as a reaction. So if for your lab you were mixing magnesium metal and HCl, then we would say that this is delta H. So any kind of math that we would do it without delta H, because this is a system. This is a reaction, this represents a system. The second part of the equation, MC delta T, we represent this by the solvent. Okay? So we just say that this was the liquid. Okay? This is the surroundings. This is what MC delta T stands for. It represents the change that's taken in the surroundings. If the question is asking you for heat flow, then you're generally looking at Q equals MC delta T, so how much heat was absorbed. But once you're looking at molar mass, then you should use this equation right here, because you have this one variable that covers moles. Okay, you'll notice that you don't have that in this Q equation right here. This is the homework. I hope you guys are doing it. If you have any questions, by all means, just hit me up on Twitter. And that concludes that. I will try to post some more videos, hopefully Sunday night for the rest of the week. Just a reminder, you have a test on Friday. Please, please, please study for that. I will try to give you a review, have it posted by either Wednesday or Thursday, and I'll have the answers up by Thursday night. Okay?